All right, so my question to you all is, yesterday, when I combined the alcohol and the water together, what did I make? A compound or a mixture? It's a mixture. Why? Well, if it was a compound, it would have the same characteristic. It would be made up of the same amount of alcohol to water. That ratio would be consistent, whether I'm here in Oak Ridge or I'm in Beijing, or if I'm in the surface of Saturn, if you could be on the surface of Saturn. But it's not. I made this to be 25% alcohol, 75% water. I could have made it 50-50. I could have made it 25-75 if I wanted to. That is a very definition of a mixture. Whenever you're mixing chemicals together, you can have any sort of proportion that you want because the chemicals are not reacting together. They're still here. Alcohol is still here. Water is still here. And because it's still water, it's still alcohol, we can use their properties against them in order to separate them. Today, what I'd like to focus in on are 5 different ways of separating mixtures. 5 different ways of separating mixtures. Now, smart people like Molly have worksheet 3.2 out. People who are not all of you are as smart as Molly. Okay? Not all, only if you're as smart or smarter than Molly should you have it out. Okay? If you're as smart or smarter, if you're not, then just leave it in your notebook. You won't need it.
I had it out.
All right. So, the first way that we're going to learn how to separate these things is called distillation. What do we use distillation for? We use distillation for separating liquid mixtures. This will be able to be separated through distillation. Who has a papaw that lives here in East Tennessee? All right, yeah. You should be familiar with distillation because your papaw probably has his own little spot back behind the yard. And Simon knows what I'm talking about. Where he practices chemistry. Odds are that Simon's papaw goes back there and he takes some corn, gets some yeast, gets some water, put some flavorings in it, and he cooks up this nice soupy material. He's going to have a wire mesh that he will then pour the soupy material through in order to pick up all the solid materials. We're going to call that filtration. We'll talk about that next. What he's going to get afterwards is a watery solution that contains mostly water with a little bit of happy juice. Now, the problem is, the way it is now, it's mostly water and a little bit of happy juice. He would like to make it mostly happy juice. So what does he use? He uses distillation. What concept does he actually use in order to separate these things? The fact that happy juice, better known as ethanol, boils at 78 degrees Celsius, while water boils at 100 degrees. In other words, ethanol will be long gone and turned into a vapor before water even considers the possibility of boiling. His papa knows about that. So, he uses an apparatus that is similar to this. Of course, his round bottom flask is probably going to be a cast iron stove of some kind. And instead of having a condenser, his papa is going to have wire, a copper tubing. You've seen those? Maybe in Dollywood. or in places where they're trying to recreate what's behind people's backyards in the forest, right? Okay, so this is called a distillation apparatus. And in this picture, they're trying to separate water and salt. Here, you have a bunch of little salt particles that are dissolved in the water. They're in there. You can't see them. They've broken up into tiny little particles suspended in water, connected to water. They've not reacted with water. Water is still water, and salt is still salt. When water boils at 100, salt thinks that the temperature is downright balmy, very comfortable. So salt won't even begin to melt until you get into several hundreds of degrees Celsius. So 100 degrees Celsius does not bother salt, but it will bother water. Once you get to 100 degrees Celsius, water vapor begins to go up the round bottom flask, and the only place it can go down is through this tube within a tube. It's called a condenser. It is a tube within a tube, and the outside, I can let water come in, and that nice cool water will flow around the inner tube, not touching anything that's inside. It is a tube within a tube. It'll flow in there and come out the other end. So you always have a nice supply of cold water surrounding the inner tube. So as your hot vapors are going down the inner tube, what starts happening to them as they bounce into the nice cool walls of the inner tube? They get into liquid form. In other words, they condense back into liquid. The salt is back here. 100 degrees Celsius is not going to affect salt any. But the water eventually will completely turn into a vapor and then completely condense on the other side. So what you have here is water down here. I'm trying to erase this. I don't know why it's not erasing. What you have down here is water, and what you have on the other side is the salt. Okay? Now, what happens in Simon's backyard? Back here, you have alcohol and water. Water won't be the first thing to boil. It'll be the second thing to boil, way after alcohol has boiled away. So the first thing to boil is the alcohol. In Simon's backyard, this tubing is exposed to the air, so you don't want to touch that tube when this thing is running because it's hot. The heat from the hot vapors is going into, is touching the, well, that is being transmitted through the tube to the outside air. So if you touch that tubing, you're getting the heat from the vapors onto your skin. All right, so by the time it gets over here to the end of this long tube, it has lost so much, the vapors inside have lost so much heat to the ambient air that what's coming out is mostly alcohol. Not entirely. Why? Have we reached boiling? No, we've not reached the boiling point of water. We've reached the boiling point of alcohol. Why is some water getting in there along with the alcohol? Marie? Nope. Alcohol does not need to absorb moisture. Ryan?
Because even though it's like, it's still, some of it's still evaporating, some of the water's still evaporating.
He's right. You know that water evaporates at this temperature at 22, right? Can water evaporate at 78? Yeah, a lot more water evaporates at 78. The problem with this process is that you can't stop water from evaporating. So even though you're getting all the alcohol over here, invariably you also collect a certain amount of water. So he may have had 25% alcohol, 75% water. Once he distills it through, it might get to 50-50. which is simply not happy enough for him. So what does his papa do? He places an X on the flask, pours this out, and what will he do? Again. Pour it back in there. Again. Now you do it again, and you succeed in getting all the alcohol and some of the water back. But what did you leave behind this time? Some of the water that you had picked up the first time. Every time you distill it, you are picking up more and more pure alcohol, leaving water behind. So after distilling it the second time, his papa puts another X. Have you seen these flasks with X's on them? That tells you how many times they've been distilled. So 3 X's means it's been distilled 3 times, and every time you distill it, that percentage of alcohol to water is increasing. I think 95% is as pure as you can make using this process. 95%. Beyond that, just you're always going to be picking up. You can't stop water from evaporating. You can discourage it, you can't stop it from evaporating. And every time you run it through, you're able to separate more and more. Any questions about distillation? Don't ask me more questions about stills. I don't. I'm not a moonshiner. Okay? Is it legal for Simon's papa to do this?
No.
Yes, actually it is. He can't sell it without a license. So if you go and ask Simon's papa for a sample, then he can get in trouble. If he just uses it for whatever purpose he wants to, whether he wants to run his car with it or whatever, that's fine. He just can't sell it.
Can he give it away?
Well, she can't. He'll get in trouble for giving it away to a minor.
Oh.
I don't know. You'll have to ask Simon. Simon's papa doesn't do this. I'm sure he doesn't. The mixture is heated until one of the components boils away from the other. The distillate is then cooled, condensed, and collected in another part of the apparatus. All right, watch as this wonderful Indian lady tells you the exact same thing that I did using an Indian accent.
Distillation. Let us have a look at the procedure of separation using distillation method. Firstly, take the mixture in a distillation flask fitted with a thermometer.
See, she's consistent. Thermometer.
Observe carefully how the apparatus is arranged. Then, heat the mixture slowly, keeping a close watch at the thermometer. See the acetone vaporizing and then condensing in the condenser. This acetone can now be collected from the condenser outlet. On the other hand, the water is left behind in the distillation flask. Do you know there are...
All right. Now, when he made that soupy mess that contained the alcohol and the yeast and the grain, the leftover grain, he wanted to get all that solid out. So what did he use in order to separate solids from water or from a liquid? Filtration, a mesh. So if you want to separate a liquid from a liquid, you use distillation. If you want to separate a solid from a liquid, you use filtration. Filtration. So, what is filtration? The process of pouring liquids through a fine mesh that allows the liquid to pass through, but not the solids. I do this every day, folks. Every day, because I am a sweet and loving husband. I don't drink coffee, but I make coffee for my wife every day. What I do is I take a piece of coffee filter. Have you heard of these things? Coffee filter is a piece of paper that has tiny little pores that are so tiny that they will not allow any of the coffee grounds to go through them. but they're so big that they will allow water molecules and things that are maybe a little bit larger than water molecules than some of the dissolved coffee molecules can go through those holes. All right, so I place the coffee on the coffee filter. I add water, and then the heating element will heat up the water and actually push it through onto the coffee. The coffee goes nowhere, but any coffee molecule that is dissolved off the surface goes with the water through the piece of filter paper. Filter paper. Some of you tried this yesterday when we were doing the polymer lab. All right, watch as this dude, notice the piece of filter paper, the funnel. He's got sand and water in here. So he's going to filter out the sand.
Careful, I'm going to use again my chemical spatula. And this time I'm placing the chemical spatula all the way down into the filter paper, right? And I'm going to pour a little bit at a time.
So the water will go through, the sand will be held back. All right. What if, well, in the polymer lab, there were times in which you just needed to get rid of some of the water and the polymers were down in the bottom. So a lot of times you've got solids that are left in the bottom and you've got a lot of water on top, and you can actually probably pour a lot of that water out before you even get close to pouring out the solids. That is called decantation. Decantation. Watch. Okay, you've got soil and you've got water. You don't want to lose any of the soil, but then again, it ain't going to go anywhere. So if you're careful, you can pour out most of the water before you get to the point where you might lose some of the soil. Decantation. Quick and easy way of separating things if you're not overly concerned with losing some of the solid. Finally, and this is one that you won't truly understand until later, chromatography. Chromatography is a process of separating different colored materials by means of the way in which it's attracted to what we call a solvent. Has anyone done this lab in middle school where you take an overhead transparency black pen, you put a little dot there, and then you let water run through it, and it separates out into different colors? You know that was chromatography. That was it. You were able to take black ink and separate it out into its different constituencies by letting water run through it. So, the process of separating colored materials. How's worksheet 3.2 going along? Oh, no, you're not supposed to be. That's homework. Don't do it now. Even though we're going through it. All right, so did you notice you separated green and yellow here? You separated green and yellow because of the way that the water ran up. The green was able to follow water a whole lot faster. Okay, last one is evaporation. I can't do this justice. I think an Indian Mickey Mouse will do much, much better.
Evaporation. You must have observed in daily life that water, when left uncovered, gradually dries up. Similarly, wet clothes dry up when spread in air. In both these examples, the water changes its state from liquid to vapors without reaching its boiling point. This phenomenon of change of liquid into water vapors at any temperature below its boiling point is called evaporation. But how does evaporation actually occur? Let us find this out. We know that particles of matter are not stationary but are constantly moving in different directions. As a result of this random motion, they collide with one another and thus possess different amounts of kinetic energy. In case of liquids at a given temperature, the particles at the surface of the liquid possessing higher kinetic energy break free from the forces of attraction by the neighboring particles and leave the liquid by getting converted into vapors. This process is known as evaporation.
What's the downfall of evaporation? It is awesome for separating solids from liquids. What's the downfall? Takes forever. Takes forever. All right, so let's recap everything we've learned in the last week. All matter is made up of either mixtures or pure substances. If you're a mixture, then you can be separated by any one of the 5, 6 separation techniques that we just discussed. But if you're a pure substance like compound, you can only be separated by a chemical reaction. That's a chemical reaction. What we just did, those are physical reactions. If you want to separate a compound into the elements, that will take a chemical reaction. All right, last target. You need to understand the power of the law of conservation of matter. Make sure your calculators are out, because everyone knows that in chemistry you should always have 2 things out. Your calculator and your periodic table. Yes, Alec? Okay. That ensures that I'm going to call on you now. Thank you. All right. What is the law of conservation of matter? No one does this justice more than Crash Course. Crash Course is an awesome YouTube series of videos. They've got one on U.S. history. They've got one on chemistry. Now, let me warn you, the chemistry one is meant for a college level, but that's okay, because I spent all summer long cutting these things into pieces that you would easily understand. Okay, the host is energetic, he's young, he's extremely nerdy, and he's funny, right? He's who? John Green. Is he somebody besides the Crash Course? What?
Is it John Green?
The what?
The Fault in Our Stars.
The Fault in Our Stars. All right, listen.
Antoine Lavoisier was pretty fantastic. He was a geologist, a botanist, a biologist, and a physicist. He helped define the metric system, created an international language of chemistry, named hydrogen and oxygen, predicted the existence of silicon, outlined what elements were, figured out how animals extracted energy from food, determined that an element could take different forms upon discovering that both ash and diamond contained pure carbon, published the very first chemistry textbook ever. And there's a reason why the law of conservation of mass used to be called Lavoisier's law. Born into a wealthy family, Lavoisier inherited a massive amount of money when his mom died when he was 5 years old. And though he did get licensed to practice law as his father expected him to follow in his lawyerly footsteps, young Antoine chose science instead. When the opportunity arose to marry a wealthy girl whose father's massive income came from collecting taxes for the French government, he did it, even though she was 13. Questionable decision, though not uncommon at the time. It turned out that the family connections would be his undoing, though not the age of the bride at her marriage. Marie-Anne, as she grew older, would become a colleague as well as a wife, assisting Antoine in his experiments and his analysis of the work of others. Indeed, it was Marie-Anne who translated an essay on phlogiston for Antoine, which he ripped to pieces, changing everything forever. Until Antoine Lavoisier started inspecting everybody's work, the prevailing theory of chemical change was that some substances contain an elusive element called phlogiston. By burning these phlogiston-containing elements, they would lose their phlogiston and become new things. Lavoisier took those theories and their research, combined it with research being done elsewhere, and added in his own genius experiments, and then tore the chemical world to pieces. with a little thing called combustion. He determined that hydrogen wasn't inflammable air, it was an element. Indeed, he named it hydrogen because it was generated from water, or hydrogenated. And he determined that oxygen was a vital ingredient for combustion and also what would later be known as oxidation, something that we'll discuss quite a lot in this course. By hooking people up to his bizarre contraptions, he determined that burning wood consumed the same amount of oxygen and produced the same amount of carbon dioxide as people consuming food and breathing, thus determining that people, and all animals, are powered by some form of internal combustion. Now, experimenters of the day, I hesitate to call them chemists, noticed that when you burn something, its mass decreased. Like, here's a fuse, and I put it on a scale, and I burn it, and its mass decreases. But Lavoisier determined that if all the particles in gas are collected, like if I burn the fuse inside a closed bottle, the mass stays the same. Stuff remained stuff. You can't lose any. You couldn't make more. This realization, though it seems obvious to us now, and its acceptance by the general scientific community, as far as I'm concerned, was the precise moment at which alchemy ended and chemistry began. Lavoisier's chief contributions and ultimately his discovery of the law of conservation of mass relied on careful measurement and careful thinking, and as you'll see, both of those things are key to success in chemistry to this day. Lavoisier the man was a bit of a dichotomy, having worked as a tax collector and helping to create a literal wall around Paris to assist in the collection of taxes, but also a supporter of the French Revolution as it began. But the enemies he had made with his wall, and by denying certain powerful politicians entry into the French Academy of Sciences, eventually caught up with him as the revolution's lunacy increased. He was beheaded on May 8, 1794. Lavoisier was pardoned a year and a half after his execution, so that's good. Marie-Anne was delivered all of his confiscated belongings, and a note of apology, like, "Sorry we killed your husband, here's all the stuff back." The mathematician Joseph Lagrange said of the event, "It took them only an instant to cut off that head, but France may not produce another like it in a century." It's worth noting, though this isn't really science talk, that Lavoisier couldn't have done any of his magnificently careful measurements had it not been for his enormous wealth. He commissioned the creation of hundreds of pieces of equipment, large and small. Only the system of economic inequality that the French were revolting against made it possible for Lavoisier to do his work. I'll leave you to think on the implications of that on your own.
All right. This guy was to the French what Isaac Newton was to the English. He was brilliant. Unfortunately, he didn't get to live out his life. His head was literally cut off by the French in the French Revolution. Even though he was actually a pretty nice guy and supported a lot of the reforms. But as you saw there, he made some big mistakes. What is the law of conservation of matter? Matter cannot be created or destroyed. That was the big deal that he came up with. And folks, without this law, everything that we're going to learn about chemistry would not have occurred. The laws that came after him, the law of definite proportion, and then finally the law of multiple proportion by John Dalton, would not have happened if it hadn't been for Antoine. In other words, are you ready, Alec? 2H2 plus O2 yields 2H2O. If you start with 10 grams of hydrogen, that's H2, and 5 grams of oxygen, that's O2, and you completely react it so that every bit of it turns into water, how much water will you have? 2 what? 2 grams. No. Try again. Yes! 15 what? Grams! How did you do that? You obeyed the law of conservation of matter. How? How much mass did you begin with? How much mass must you end up with? 15 what? Grams. You're really into porn, aren't you? Into naked numbers. 15 is not good enough. It's 15 what? Grams. 15 grams. That's it. That's the law of conservation of matter. The law of conservation of matter. Whatever you begin with, that's what you must end up with.